Spack handles the process of downloading a tool, all the dependencies that you need to build the tool, which could be tens or maybe hundreds of other packages, and putting all that together and making sure that they are linked and optimized for the machine that you're trying to build for.
This is episode 25. For this chat, we have Todd Gamblin of Lawrence Livermore National Laboratory, LLNL, to talk about Spack, a popular high-performance computing package management tool. Todd is a computer scientist in the Center for Applied Scientific Computing at LLNL. His research focuses on scalable tools for measuring, analyzing, and visualizing parallel performance data. Todd leads LLNL's DevRAMP, Reproducibility, Analysis, Monitoring, and Performance team, and he is the creator of Spack. Welcome, Todd.
Hi. How's it going?
It's going great. LLNL recently published an excellent article about Spack, and we encourage you, the listener out there, to read the piece, which is by Jeremy Thomas. The link is on ECP's website. The article points out that Spack is considered to be a lab-developed app store for supercomputers. Todd, let's begin by having you tell us what that means and why Spack is becoming a standard bearer.
So we said Spack's an app store because I think that's the thing that people most relate to. If you're on your phone, you use the app store to get software, and you pretty much click a button and have it. The analog for HPC is a little more complicated. We don't download binaries. We build things from source and we optimize them for the architecture. So Spack handles the process of downloading a tool, all the dependencies that you need to build the tool, which could be tens or maybe hundreds of other packages, and putting all that together and making sure that they are linked and optimized for the machine that you're trying to build for.
Okay. ECP now has adopted Spack as the deployment tool for its software stack, which is what ECP's software technology research focus area is developing to meet a broad spectrum of applications and workloads. Could you tell us more about Spack in ECP?
So the use of Spack in ECP dates back to Mike Haru's XSDK project, which I think you have another podcast on. XSDK was an effort, or continues to be an effort, to put together the major math libraries into a single package that a user could download and use very easily. The problem with that is that you have to build all of those things for all these different machines that we're trying to address under the Exascale project. So you might need to build 10 packages plus their dependencies for Titan or for Livermore Sierra machine for Summit, for Theta at Argonne, all these different systems. And that can be pretty complex. So XSDK was an effort to periodically release versions of those libraries that work together well in a single build. And we used Spack to automate that process. So basically everyone on XSDK would get together and write a recipe for their package, and we would iterate on that until we could take the resulting recipe that we committed to Spack and just type Spack install XSDK on all those machines and have all the packages installed. So it automates that process. The XSDK approach, I think it was really useful for bringing these teams together and having them work out common build issues, which can be pretty nasty for HPC. And they're typically things that only the developers of the software really know well. But if you want people, if you want regular scientists to be able to pick this stuff up and use it, then you need to make sure that they don't run into those things and that they don't have to basically debug the problems that the developers would need to deal with. So this process of getting the developers together, having them work together on a release, hashing all the bugs out and making sure there's a stable version out there, is something that we started with XSDK and that now lots of different teams are doing under ECP, under more general SDK projects. So in this context, SDK stands for Software Development Kit. So as a whole, ECP is planning on taking all of these independent SDK releases, putting them together, and making that into the overarching ECP software release. And the idea is that would make it easy for anyone to pick up the things that we're developing under ECP and install them using Spack. So Spack is the vehicle for all these SDK releases. Basically, the teams get together, they work on their packages, they commit them to Spack, and then they're available for anyone using Spack to install on HPC machines.
Todd, the article I referenced earlier does a nice job of delving into the origins and evolution of Spack. Will you speak to that?
Sure. So Spack is kind of a project born out of anger at the complexity of building things for for HPC machines. I've had a bunch of grad students who I mentored, and they would have to build lots of software as part of their day-to-day work. But that's not the focus of the research. That's not the actual science they're trying to do. It's kind of grunt work, and it's stuff that's actually hard to debug. You only learn to fix these build issues through experience, and there's not a lot of documentation on it out there. So I created Spack to automate the 10 or so packages that one of my grad students had to build for BlueGene Q here at Livermore, because it just got to be really painful. Every time the system software stack changed on the machine, we would have to rebuild all the packages so that they would work with the latest MPI, the latest runtime libraries, and that really helped out there. I think shortly after we had Spack working for that case, we started using it for production Python deployment at Livermore, and it sort of broadened from there to where we were using it to deploy more and more user software. Once we put it out on GitHub, I think that plus the SC paper that we wrote on it really helped get people interested in the tool, and so we started getting lots and lots of contributions from outside. So I think when I actually put Spack on GitHub in 2015, or I guess it was 2014, and then by the time of the SC paper, we had around 170 packages in it. And since then, I mean, it's just grown to where we have 2,800 or more now, so almost 3,000 packages in the tool. And most of those are not contributed by Livermore. I think we're at something like less than 15% of the total packages in Spack now. They're mostly contributed by outside organizations, and we have over 300 contributors. So, I mean, it's a common need. It's addressing a pain point for many people who use these clusters, and I think we're leveraging the wisdom of the crowds, right? If one person finds a build problem, they go and commit it to Spack, and they don't have to deal with it again, and also anyone else who uses that package doesn't have to deal with it again.
Can we get a little bit more specificity about the overall benefit? You were talking about this a little bit, about the overall benefits and advantages, avoiding redundancy and all those different things.
So there's a lot of advantages, and I think other domains like most Linux distributions, lots of programming languages are starting to have package managers, where for APT or for RPM, there are binary packages that get checked in, and people are probably used to installing those in their Linux distribution. They can just say apt install something, and then they have it on their system. One of the problems with those systems is that they require root. So basically you have to be a super user in order to install packages. And we don't let people be super users on the supercomputers. Most people are running as themselves in an unprivileged account, so they can't use package managers like that to manage their software. Mm-hmm. The language-specific package managers, I think, are closer to what developers need for an HPC workflow, but they're language-specific, and most of them are for high-level languages like Python or Ruby. And we're trying to put things together that span those languages plus C++, Fortran, C, and other types of runtimes like MPI and lots of math libraries. So Spack provides an environment kind of like those systems, but it's more flexible in that the packages are templated. You can build them from source. It lets you really optimize things for HPC systems, and it spans the full package ecosystem that we care about for scientific computing.
Spack has a healthy user base and significant presence in the GitHub community. You've already talked about that. Can you tell us a little bit more about that?
Sure. So, I mean, I talked about this a little bit before in that now we have all these contributors on GitHub. I think, it's been a very interesting process because we're not really developing Spack just for ourselves. We're building it for a larger community, and we want it to be used across HPC. And I think that philosophy and having that from the start has helped us because, we really try to engage users and keep them contributing to Spack on GitHub. So, we've worked with folks from Fermi and from CERN. They've contributed major features like binary packaging. They've been really helpful. We have good collaborations with the other national labs, and in some cases we've gone to great lengths to support their machines, even if we don't have them at Livermore. So we've done a lot to support Cray machines just to make sure that everyone's included in the Spack community. And I think that general approach has gotten us more contributors. Like if we see someone who could be a potential strong contributor to Spack, we'll go and try to help them out and keep them in the community and make sure the tool works for them. And that keeps them contributing packages back so that when we need them, we can use them as well. And so I think this is a great way to manage things for projects under ECP, because we have so many organizations that can collaborate together.
Fantastic collaboration. Spack can be used even on laptops and home computers, right?
Yeah, so we support Mac laptops and Linux machines right now. We would like to support Windows at some point just to broaden the potential user base. And also there's a lot of scientific computing users who want to run under Windows. But we haven't, we haven't put that at the top of our priority list yet, but it's definitely on there.
Mm-hmm. If we may, let's wrap up our chat with a few words from you about the plans for Spack, adding features, expanding its community, and so on.
So Spack builds packages from source right now, and it can take a while to install things. If you build, Trailing it may be a few hours before you actually have that package installed. And so one thing we're trying to do is increase the number of packages for which we provide binaries. So this past year, we've worked with Kitware to deploy infrastructure in the cloud that will basically look at the Spack repo, see what packages are coming in, and automatically build binary packages and make them available to people. That doesn't necessarily mean that, I don't think we can build every combination of and every configuration of all the packages in Spack, but we're hoping that we can have a decent binary distribution in there so that you could potentially build a stack in minutes. And that, or at least put it together, right? You wouldn't have to build it. The other feature that we're trying to add is support for environments. And so recently we've added the ability for a user or a developer to basically provide a list of the dependencies they care about and have them all installed in a single environment at once. And we think this will increase reproducibility across the machines. For next year, we're really focusing on facility deployment, and so we're working with the hardware integration part of ECP and the facilities to simplify the workflow for people deploying large software stacks for users at HPC facilities. So the idea there is that a user could log in to, say, Summit, and if the facility has deployed a bunch of software and the user wants to build something slightly different but that leverages all the software that's already installed on the system, they could put that together very quickly and have, tens or hundreds of dependencies coming from the system installation and a few custom ones of their own leveraging that without actually having to build any of that themselves. So, that's where we're going. We're trying to simplify the workflow for HPC users across the board.
Excellent. Well, thanks, Todd. We appreciate your joining us today.
All right. Thanks a lot.
Our guest has been Todd Gamblin, a computer scientist in the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. Thanks a lot to you, the listener, for joining us. And this is Scott Gibson for the Exascale Computing Project and Let's Talk Exascale podcast.